How's it going, Mickey?
It's going good, Rocky. Are you ready for your final test?
I'm ready, Mickey. I'm ready.
Alright, let's do this. Now, I have 3 problems for you to solve. The first one that I want you to solve is a representation of the Marston Water Tower. And within that, I want you to find the equation for the change in height of the water in the tower.
Alright, well, the tower is a tank. There's obviously a pump to get the water up to it, and there's also a flow rate out of the tank. So I know the first step in doing this is to draw the diagram and the free body diagram.
Alright, good.
So I'll start by drawing the Marston Water Tower represented by a simple tank with some water in it. The height of the water within the tank was going to be labeled H.
Very good.
Now the tank is suspended above ground for pressure reasons, and there's a pump with pressure P sub S pushing the water into the tank.
Yes.
The length from the bottom of the tank to the ground we can label as L.
Yes.
There's also water coming out of the tank at a flow rate Q out. A mass flow rate Q out, QM out. So, the first things we're
What else are you missing, Mickey? Or Rocky?
P, we know that this is exposed to the atmospheric pressure, and we know that at the bottom of the tank, pressure is, we can label that pressure sub PT. Yes. We know the pressure after the valve, or at the very, very bottom, can be PB, and we know the pressure before the valve is PS. And here is where we have our mass flow rate in.
Very good.
Now that we're done with the free body diagram, we move on to the finding unknowns, which is our pressures. So we know that the pressure here at the bottom of the tank, PB, is equal to the pressure at the top of the tank plus density of water, gravity coefficient, and the height L, which we labeled as the height of the bottom of the tank. Secondly, we know the pressure at the top of the pressure at the bottom of the tank is equal to density times gravity times the height of that tank plus the atmospheric pressure which it is exposed to. Combining those two equations, we can get pressure at the bottom of the tank is equal to rho GH plus rho GL plus PA.
Very good, Rocky.
Now, the next thing to do is to analyze each component of the system. So I'll start by analyzing this component of the system, the valve. So the governing equation for the valve, the mass flow rate through a valve is mass flow rate through a valve is equal to PA minus plus PS minus PB, all over the resistance within the valve. So you plug your pressures into the equations and you come up with PA plus PS minus rho GH minus rho GL minus PA. So the plus PA and the minus PA cancels, and all that is over R. Lastly, we'll look at the third component of our system, which is the tank. The governing equation for the mass flow rate out of a tank, dm over dt, is equal to the mass flow rate coming into the tank minus mass flow rate going out of the tank. that is based on conservation of energy. We also know that the mass flow rate of the tank with respect to time is equal to CPT dot, which is the change in pressure at the bottom of the tank. So we know PT dot equals rho GH dot. So now that we know what rho GH equals, we can plug it back into our original equation and we can get CPT dot equals PS minus rho GH minus rho GL all over R minus Q mass flow rate out. So C rho GH dot is then equal to PS minus rho GH minus rho GL over R minus Q mass flow rate out. And then that is the final equation for the height of the Marston Water Tower.
Awesome. Very good, Rocky. Very good. That was a good example. Alright. Ready for your next one?
I don't know, Mickey. I think so.
Well, you're off to a good start, so let's try it. Alright, the next one is I want you to solve the system for a generator in terms of KE theta dot and your resistance of the system.
Alright. Well, first things first is you draw the free body diagram. So the governing equation for this loop based on Kirchhoff's law would be equal to the VEMF of the generator minus the voltage drop across the resistor minus the voltage drop across the other resistor is equal to 0. There's Kirchhoff's law, just for this circuit. Then VEMF minus RMI minus VEXT equals 0. So then if we isolate this circuit into just one circuit, it would look like this. And then the governing equation for that simple circuit would be R effective is equal to R sub M plus Rext. Then that simplifies down. Oh, there also the voltage drop equation is equal to VEMF equal to R effective times I. That's
Yep, very good, Rocky. That accounts for both the resistors that you combine together.
I see. So then in that equation you solve for I and you get VEMF over R effective. So you plug that back into the first equation and you get VEMF equals minus RM EMF over R effective minus VEXT equals 0. And then we know from the original equation that VEMF equals KE. So then you can plug that in and you got KE theta m dot minus RM times KE theta m over R effective, which is effective resistance for the whole circuit, minus VEXT is equal to 0. So then that is the final governing equation for this in particular circuit. How's that look, Mickey?